Everyone, welcome back to another day, another Leetcode. My name is Timothy Lee Grant, and let's get started. So, what do we want to do today? How about we do a union find? Let's see about a union find. I'm gonna minimize myself, make it a little bit less. What's that problem? That one's a medium. I don't want that. All right, let's go, go, go. Oh my gosh, they're all hards and mediums. Perhaps we're not going to. Oh, here we go. So we are going to do a union find. Okay. All right. Let's get started. So, number 1971, and all of a sudden my little senses are going, wait, hold on. That's a big number. Usually big numbers are difficult, but we're going to see about this. Find if path exists in graph. Okay, let me turn there. I can see the screen better now. There is a bidirectional graph within vertices. Okay, a bidirectional graph. I think that means that each edge connects both ways. So it's like a non-directed graph. I think that's what it's meaning. Within vertices. Okay, vertices are the little actual nodes here. Okay. Where each vertex is labeled from 0 to n minus 1 inclusive. Okay. So we have n right here. And each of these vertices are going to be labeled with a number starting from 0 all the way to n minus 1. Okay. Now, the edges in the graph are represented as a two-dimensional integer array edges. Okay, so what is that? An edge list, right? Like this. That means that there's an edge from 0 to 1, so that's edge list, yeah. All right. And then this just says that edges of I means that there's an edge between them. All right, whatever. That's what we just said there. Denotes a bidirectional edge between the vertex U. Yeah, okay. It just means that they're connected. Okay. All of this to say 0 and 1 are connected. Okay. Every vertex pair is connected by at most one edge. So every vertex pair. What does that mean that? What does it mean a vertex pair? So every single element, every single vertex is connected to every other element? Is that what it's kind of getting at? And no vertex has an edge to itself. So I think that means like a loop. So from 1 back to 1. You want to determine if a valid path exists. You want to determine if there is a valid path that exists from vertex source to vertex destination. So apparently, my idea of every vertex pair is connected by at most one edge is wrong, because if this statement actually did mean every vertex is connected to every other vertex, there would always be a path from one to the other. And not only that, there would be a direct path from one to the other. So apparently that's not what it means. So given edges and the integer n, source and destination, so these are the things that we're given. We're given the edges list. We're given n, which is the number of vertexes or nodes. We're given a source node and a destination node. We want to return true if there is a valid path from source to destination, or false if there's not a valid path from the source to the destination. Okay, so kind of understand the idea. So what are we doing? N is 3. Edges are 0 and 1. So 0, 1. 1 and 2. So 1 and 2. 2 and 0. 2 and 0. Okay? Source is 0 here. Destination is 2. So there is a path, right? There are 2 paths, yep. So you could go here to here or from here to here. Okay, so yeah, here we have like 2 not connected graphs, right? There's no connection here or here. So we want to go from 0 to node 5, but we can't come here and we can't come here. Okay, so thinking about how to do this, I am going to see if possibly I can try to take that edge list and turn it into like an adjacency list. Would that help me? I guess, because then I could do a depth first search on that graph, right? So I guess let's do that. So, okay, thinking back, how do you actually change a edge list to an adjacency list? Okay, so I know that I need to loop through each of the elements in this edge. Okay, so while for edge in edges, so I'm going through each of the elements in edges. A B equals edge. Okay, so edge here is going to be one element in this list, which is edges. And so edge here is going to be comprised of 2 parts, which is 1 and 2. And I'm just going to store those variables in variables called A and B. So the 0th index will be stored in A. The 1th index will be stored as B. Okay. So now what do I want to do? I want to connect those two. So I need to say like adjacency list A dot append B. So right now what I'm doing is I'm just writing the thing that I want to do, and then later I'm going to figure out like how to actually implement that. So I'm going to get this adjacency list such that this works. Right now I'm just trying to write down what it should be. So I also want to do adjacency list B append A. So I'm connecting A and B together. Or I'm saying that A is connected to B, and then I'm saying B is also connected to A. Okay, so now I need to create this adjacency list is equal to an empty list, but that's not true. Okay, so what is this actually going to be? So I'm indexing this adjacency list, and I'm appending B. So let me write a comment. I know what I need to do. I'm just going to, here, let me show you kind of what I'm going to do. For in range in. Like this. Okay. So what I'm going to do is this adjacency list is going to be an array of empty arrays up to n, and let's say n is 3. So uh, 0, 1, 2, 3. Okay? Now, this list means that the 0th element is connected, the 0th element, or 0th node, is connected to nothing, right? So it's connected to nothing. The first element, the number 1th element, is connected to nothing, or yeah, connected to nothing because it's an empty list. Then the second, number 2, is also connected to nothing because it's an empty list. And then vertex number 3, this graph doesn't have vertex number 3, but if it did, it would have a value of, or it would be connected to nothing because its adjacency list is empty. So this is adjacency list right here. Okay, so the way that I did that was just creating an empty list. So an empty list here, but then I'm populating this empty list with what? With an empty list right here. And I'm doing that. How many of these am I creating? I'm creating n of them, right? So 4 and then blank. I'm not doing anything. I'm just auto inputting this blank list. Okay. Then what I'm going to do is I'm going to get an edge. So I'm going to get this 0 and 1. And now I am going to store 0 as A and 1 as B. Okay. So then what I'm going to do is I'm going to take my adjacency list of 0, which is going to be this one right here, right? And I'm going to add B, which is 1. So that means A, right here, 0, is connected to 1, right? 0 is connected to 1. Awesome. Now I'm doing B, which is 1. So that's this one here. I'm indexing B. Append A, which is 0. So 1 is connected to 0 because it's bidirectional. So that's what I'm doing, and I'm doing that for each of those edges. So now, at the end of this for loop, I should have a list that contains, each index contains that specific node's connections. Okay, so now what do I want to do? I want to do a depth first search, right? Starting at source, and if I get to destination, I stop. Good. So how do I do that? I need what was it, a stack, right? Stack equals here. The other thing that I want to do is I just want to, if not edges, is that true? I'm thinking like this, return false, but what if there's source and destination are the same? So, okay, I'm going to do it like this. If source equals destination, we return true. Okay, so if we say the source is 0 and the destination is 0, we just return true. Then we say, okay, so right here, now if this line of code executes, we know that this line of code is not true. So source is not equal to destination. So now I say, if we know that we're not at the destination yet, if there's no edges, nothing is connected to anything, then we know that we cannot go from our source to our destination because we know that we're not currently at our destination, and we know that there's no paths at all. Okay? All right. So, now, stack.append. What do I want to append? source, right? Source. And so what is source going to be? Source is going to be an integer representing the node that I'm currently at. Okay. No, I don't want to append source. I want to append all of the connections which source currently has. So I can get that by accessing this adjacency list. So I can go adjacency list indexed at source, right? And now this is going to get a list of what? It's going to get a list of elements. Either it's, for example, it could be, let's say source is 0, and 0 has 2 and I don't know, 3, right? So it's going to get this list right here saying that 0, I can try node 1, I can try node 2, I can try node 3. So those are the nodes which I'm allowed to visit because source, where I'm currently at, is connected to those 3 elements. So this is, I'm going to put a list inside of my stack. Okay, so now while stack, so while my stack is not empty, what do I want to do? I want to that's a good question. What do I want to do? What do I want to do? I want to like add it somehow. What am I even talking about? So I want to add all of the elements that I have, right? What does that even mean? No, I want to pop from my stack. I want to take an element from my stack. Okay, so current element, current, maybe, I don't know, list, current thing, not a very good name. Anyways, it's okay. The current thing is what? Is stack dot pop. Okay, so I'm popping, and now current thing is a list. Current, and I'm gonna put that in a comment. So current thing. I'm just gonna call it current. Just current. Current is now going to be equal to a list, and this list is going to have 1 and 3 and 2. Okay, so these are the connected nodes. Okay, so now what I do is I want to go through all of the elements in current, right? So for element in current, okay, and now I want to add each of those connected to it's just getting more complicated. I don't know if I'm doing this right or if I'm going down a dark path, but not a dark path, like if you're in a dark forest, right? If you're going down a mysterious path, right? Maybe I'm on a dead end path or something. Don't quite know yet, but we're gonna see. We need another glass of water. All right, so element in current. Stack. Well, first, I don't want to keep adding elements if I've already added them, right? So if we have like a loop where here I don't want to add 1 and 2, and then here I add 0 and 2, Here I add 0 and 1. Here, and then I come back to here because I keep putting all of the elements back into my stack. I don't want that. I want something like visited. So if element not in visited, then stack dot append element. Oh, but element is going to be a singular. And this is a list. So this one is going to be a list, right? So I'm putting a list here into my stack, and I'm popping current, which is going to be a list, right? Like it's all the edges associated in it. But then here I'm putting in my stack a singular element. Whatever. Maybe I just do like adjacency list element. Oh my goodness, I don't even know what I'm up to. So what? Well, I don't even think I'm on the right path. So, okay. Let's get rid of that. I'm not on the right path. Okay. Let me think through a little bit better of what I want to do. I want to go from here, so 0, and I want to, actually, I guess maybe I should do a breadth first search, right? Maybe. It doesn't matter. I don't think it matters. So I want to come here. Okay. So I want to come here. No, first I want to put this in visited. So I need some kind of like visited is equal to a set like this. Okay. So I want to put this current element. So visited dot add and then source. Okay. Now I want to go from here to here. And then I want to add this. And then I want to add all of its children, or all of its connections, right? So I still think I need that stack. It's equal to an empty list, okay? So now I want to add all of the elements in source. So for does Python have like a do while? No, it doesn't. It's not keyword. There's no keyword when I do. So I guess Python doesn't have a do while. So I want to, come on, think. I'm just gonna solve this the strange way. So for connection in adjacency list indexed at source. Okay. Stack dot append connection. So now I'm looking at the specific. Let's say source is 0. So we're starting at node 0. I'm going to look at the 0th element in my adjacency list. I am going to get each of those elements. So 1, 2, and 3, and I'm going to just put that in my stack. So those are the available ones that I can go to. So now I want to do so now stack is going to be populated. So now I can do while stack. So now stack is not empty, and I want to stop when stack is empty. Okay, so now what I can do is I can just current, so that's the element that I'm currently at, is going to be equal to stack.pop. Okay, so I take out an element. So here I have 0 and it's connected to 1 and 2. So on my stack I have 1 and I have 2. Okay, so now what I want to do is I want to take out this 1 from my stack. I want to see, have I already visited it? So if current in visited, then I want to continue. Okay. If it is not the case, so now it means that it's not in my visited. So I want to visit this. So visited dot add current. So now I'm putting it in my visited, and then I want to add all of visited's connections, right? So for element in adjacency list indexed at current. Okay, so I'm looking at the current element, which might be this one, whichever node. So I'm at 1, so I'm going to be looking here. So I'm going to say, okay, there's 0, so I can go to 0. So I'm going to add each connection that my current node has. So stack.append element. Okay. The other thing I want to do is if current is equal to destination, then we return true, because we got to the destination. So if our destination was 1, and we come here and then come here, and now my current is here at 1, I say, all right, we achieved it, so we stop. Okay. So we added all of the elements back. We added all of the elements that were currently, the node that we're currently at, we added all of its connections to our stack. Then we're going to come back up here, pop the next element from the stack. Okay. And we're going to do that until our stack is empty. So then, if we come here, once we pop out of the while loop, then we can return false. I don't know if it's going to work. Okay, ADJ. Okay, let's Let's see if it works. Oh, okay. Wow. That's a little bit surprising. Now what I'm a little bit curious about is there was this thing. It's called union find, but I don't feel like I used union find, right? So that is going to be my next question. So I'm going to take this over to GPT and ask it, here is my solution to this one. What do you think of it? Any other methods to solve it? Okay, let's see what GPT has to say. Your solution looks solid. It's a depth first search approach using an adjacency list to represent the graph, which is an efficient way to solve the problem. Here's a slightly cleaned up version. So this is the same, this is the same, adjacency, that's the same. For A, B, and edges. What is this doing? A, B, and edges. Oh, okay, that's the same thing that I'm doing here. Yep. Good, that's the same. This is the same. Oh, I'm just adding source. I can just add. Yeah, that makes sense. I don't need to add all of sources connections immediately. I can just add source and then go into the stack. Yeah, makes sense. So now I pop the next element in my stack, and that's my current, and then I say if it's the destination, if current not in visited, or if it is in visited, I continue. If it's not, I add the current node to visited, and then I do stack extend. Okay, so this extend is just going to be a different methodology for doing this, like add all the elements in a list. Okay, and then return false. So breadth first search, I think this is like the exact same thing, but it's with a Q. Okay. Union find. This is what we're here for. This is the question of the day. This is need to switch my cups. All right. So union find. This approach is useful for problems related to connectivity. It allows you to keep track of which nodes are in the same component. Okay? So I'm creating a list. Okay. And parent. Okay. Find of, so I'm declaring two functions, find and union, or union and find. Okay. If parent indexed at x is not equal to x, parent x equals find parent x. Okay. Union. So I'm doing recursion here. Return parent. Union x and y. Root x equals find x. Root y equals find y. To be honest, I think I'm too tired to actually dig into this. I feel so lazy for saying that, But I am. I am. Oh, come on. What's going on here? Return find source equals find destination. My well, yeah, I don't know. Right now, like what's going through my head is, do I have the necessary energy to actually take take this on right now, or do I just kind of not? Oh. Find. I mean, so what do I do? 4A, B in edges. So edges, I'm just getting those. Where are I? Edges. This is connected to that. Okay, so A and B are connected. I connect them maybe. I don't know. Union is going to find X. Why do I need to find X? What does that do? Root X. Okay. Find X. So I put 0. So 0 and 1. I put 0 in here. If parent of does not equal X, I recur. Yeah, I don't know. That's one of the problems. Coding at like 10 o'clock. I don't know. I think I'm just gonna call it tonight. Yeah, I'm. Yeah, sorry. Anyways, I hope you guys have a good rest of the day. And thank you for watching this video. My name is Timothy Lee Grant, and I will see you again tomorrow with another Leetcoding video. Yeah, I feel kind of bad because it's like being completely lazy, and I just don't have the energy to look at this. I don't have the energy to do it. Okay. Goodbye.